Welcome to this video on the history of the atom. We will explore how our scientific understanding of atomic structure has evolved over the last 2 centuries, moving from simple spheres to the complex nuclear models used today. In this video, we'll examine 4 key milestones: Dalton's solid sphere model, Thomson's plum pudding discovery, Rutherford's nuclear model, and the modern understanding of the atom, including Bohr's work and the discovery of the neutron. We begin with Chapter 1, John Dalton and the birth of atomic theory. In 1803, John Dalton proposed that all matter is composed of tiny, indivisible particles called atoms. He suggested that atoms of the same element are identical, while those of different elements have unique properties and combine in fixed ratios to form compounds. Dalton's model depicted atoms as hard, solid spheres, much like miniature billiard balls. He argued that these atoms were indestructible and could not be split, created, or destroyed during chemical reactions. Dalton's work was a significant scientific breakthrough. By moving the concept of the atom from philosophical speculation to a framework based on measurable chemical data, he provided an explanation for the law of definite proportions. However, the limitation of Dalton's model was the assumption that atoms were indivisible. Later observations, such as electrical phenomena and specific light emissions, suggested that there was an internal structure yet to be discovered. This leads us to Chapter 2, J.J. Thomson and the discovery of the electron. In 1897, J.J. Thomson experimented with cathode ray tubes. He found that these rays were deflected by electric and magnetic fields, proving they consisted of negatively charged particles smaller than any known atom. He had discovered the electron. By measuring the deflection of these beams, Thomson calculated the charge-to-mass ratio of the particles. His finding that they were significantly lighter than hydrogen atoms provided definitive proof that atoms contain smaller internal components. Following this, Thomson proposed the plum pudding model. He visualized the atom as a sphere of diffuse positive charge with negative electrons embedded throughout, like fruit in a pudding, keeping the overall atom electrically neutral. In this model, the atom was seen as a solid, continuous structure. There was no concept of a hollow center or a dense core. The positive charge was thought to be spread uniformly across the entire volume. Thomson's model was a major step forward, as it proved the atom was not indivisible. His work earned him the Nobel Prize in Physics in 1906, though his model would eventually be challenged by future experiments. Now we reach Chapter 3, Ernest Rutherford and the famous gold foil experiment. In 1909, Rutherford, Geiger, and Marsden tested the plum pudding model by firing alpha particles at an extremely thin sheet of gold foil. Gold was chosen for its ability to be beaten into a layer just a few atoms thick. Rutherford based his expectations on the plum pudding model, believing positive charge was diffuse. He expected alpha particles to pass through with only slight deflections. However, the actual results were startlingly different, revealing that something far more dramatic was occurring within the atom. The experiment yielded 3 key observations. First, most particles pass straight through, suggesting the atom is mostly empty space. Second, some were deflected, indicating a concentrated positive charge. Finally, a few bounced straight back, as if striking a dense center. This visualization shows the experiment's results alongside the proposed model. The path of the alpha particles confirms that the atom is not solid, but rather consists of a tiny, dense, positively charged nucleus surrounded by vast empty space. Rutherford himself famously described the surprising results. It was as if one fired heavy artillery shells at tissue paper and they bounced back to hit the shooter. This leads us to Chapter 4, Rutherford's nuclear model, which revolutionized our understanding of atomic structure. In 1911, Rutherford proposed that the atom's mass and positive charge are concentrated in a tiny nucleus at the center. This model explained the particles passing through, the deflections, and the backscattered alpha particles. The nuclear model accounts for our observations. Empty space allows passage, proximity to the nucleus causes deflection, and a direct hit results in a particle rebounding. Comparing Rutherford's model to Thomson's reveals a major shift: the transition from a diffuse, uniform distribution of charge to a model featuring a dense, centralized nucleus. However, Rutherford's model faced limitations. Classical physics suggested an orbiting electron should continuously lose energy and spiral into the nucleus, causing collapse. Additionally, it couldn't explain the discrete wavelengths in atomic emission spectra. These challenges lead us to Chapter 5, Niels Bohr and the introduction of fixed energy levels. In 1913, Niels Bohr modified Rutherford's model. He proposed that electrons occupy fixed energy levels, or shells. By jumping between these specific levels, electrons explain both the stability of atoms and the characteristic light they emit. Bohr's model visualizes electrons orbiting in shells. These levels have fixed energies, with those closer to the nucleus holding lower energy. For GCSE chemistry, it is important to remember the first three shells accommodate 2, 8, and 8 electrons respectively. Bohr's contribution was crucial because it resolved the stability problem, explained why atomic spectra consist of specific lines, and introduced the concept of quantized energy packets to the atomic model. Finally, we arrive at Chapter 6, James Chadwick and the discovery of the neutron. In 1932, James Chadwick addressed the, quote, missing mass problem. By bombarding beryllium with alpha particles, he identified a neutral particle with mass similar to a proton. This particle, the neutron, completed the modern picture of the nucleus. Let's explore what the discovery of the neutron explained. It accounted for the quote mass in the nucleus that protons alone could not explain, and identified why isotopes exist. Atoms of the same element can have different numbers of neutrons. Furthermore, neutrons help stabilize the nucleus by separating positively charged protons, reducing their electrostatic repulsion. This brings us to Chapter 7, the modern atomic model. The modern model combines the insights of Dalton, Thomson, Rutherford, Bohr, and Chadwick. It describes the atom as having a small, dense, positively charged nucleus containing protons and neutrons, while negatively charged electrons orbit in fixed energy levels or shells. Here is a breakdown of subatomic particle properties. Protons and neutrons are found in the nucleus, with relative charges of +1 and 0, respectively. Electrons exist in shells with a charge of -1 and have negligible mass compared to the nucleons. Atoms are incredibly small. A typical atom has a diameter of about 0.1 nanometers, and the nucleus is roughly 10,000 times smaller than the atom itself. This vast scale explains why most particles passed through the gold foil during Rutherford's experiments. We now look at Chapter 8. How scientific models change. The history of the atom shows that scientific models are not permanent truths. They are the best explanations based on current evidence. When new data contradicts an existing model, scientists must revise or replace it through a cycle of testing and evaluation. Each model changed due to new discoveries. Thomson found electrons, replacing Dalton's solid spheres. Rutherford's gold foil experiment replaced the plum pudding model with a nuclear one. Bohr used spectra to establish energy levels, and Chadwick's discovery of the neutron finalized the nuclear composition. This timeline illustrates the progression from simple spheres to our current complex understanding of the atomic structure. Finally, let's cover some essential exam-focused tips. Rutherford's experiment is a common GCSE topic. Remember the 3 observations. Most particles pass through, meaning the atom is mostly empty space. Some are deflected by the concentrated positive nucleus, and very few bounce back, indicating a dense, tiny center. Avoid common mistakes. Don't confuse atomic number with mass number. When discussing the gold foil experiment, note that only a tiny fraction of particles bounce back. Always link your evidence clearly to the conclusions drawn. Quickfire recap. Dalton proposed the solid sphere. Thomson discovered the electron with his plum pudding model. Rutherford identified the dense nucleus, and Bohr defined the energy levels. Key vocabulary includes the nucleus, the electron, alpha particles, atomic number, mass number, and isotopes. These terms are foundational for describing atomic structure correctly. In summary, the story of the atom is a journey from Dalton's spheres, through Thomson's pudding and Rutherford's nucleus, to Bohr's levels and the modern model. Understanding these shifts helps us appreciate the scientific process.